In this video, we're going to be looking at the properties of giant covalent substances. Now, for the AQA specification, you need to be able to discuss the properties of diamond, graphite and fullerenes. And although there is some similarities between them, there's also some subtle differences. So you need to be careful when you're discussing these in exam questions. So, let's start off with diamond. Here's a diagram showing the structure of diamond. And what are the properties of it? Well, diamond has a high melting point and high boiling point. It does not conduct electricity and it's extremely hard. Now we need to be able to explain these properties by looking at the structure and bonding within diamond. So, first of all, if we look at how the carbon atoms are arranged, okay, this is known as a tetrahedral shape structure, and each of the carbon atoms is bonded to 4 other carbon atoms, okay? Now, if you remember rightly, carbon's in group 4 of the periodic table, so that means it's got 4 electrons in its outer shell. So, because it's made 4 covalent bonds, that means all its outer electrons are involved in bonding. So, the carbon atoms in diamonds have no delocalized electrons, and because they've got no delocalized electrons, that explains why diamonds cannot conduct electricity. As I've previously discussed, all these carbon atoms are covalently bonded together. Now, covalent bonds, like all chemical bonds, are extremely strong. A covalent bond is an electrostatic attraction between a shared pair of electrons and the nuclei of each of the 2 atoms. So, because these covalent bonds are so strong, if you want to break them down when you melt it or boil it, you'd have to put a lot of energy in to break them bonds. And because you have to put a lot of energy in, that is why diamond has high melting points and high boiling points. So, if we're looking at graphite, what are the properties of graphite? Well, graphite also has a high melting point and a high boiling point. It does conduct electricity, and graphite exists in layers, and individual layers can be removed quite easily. Now again, we've got to explain these properties by relating it to the structure and bonding found within graphite. So if we look at the structure of graphite, okay, it's arranged, the carbon atoms are arranged in a different way, okay? They're arranged in these hexagons in layers. And if we look at each carbon atom, it's bonded to 1, 2, 3 other carbon atoms, okay? If we look, again, it's covalent bonds between these carbon atoms, and covalent bonds are strong, okay? So if we want to break these bonds, again, we're going to have to put a lot of energy in to overcome these bonds, and that explains why graphite, just like diamond, also has a high melting point and high boiling point. Okay. If we're looking at these, why these layers can be removed easily, okay? Well, if we look at these layers, although there's strong covalent bonds between the carbon atoms within a single layer, actually in between the layers, what keeps them together is only weak intermolecular forces. So these dotted lines here represent the weak intermolecular forces in between the layers, and these layers, these forces are so weak that it's very, very easy to break them. In fact, this is why we use graphite in pencils. Just the force of you moving the pencil across a piece of paper is enough to overcome these intermolecular forces and leave a layer of graphite on your paper, and that's why we use graphite in pencils, so they can be removed very, very easily. The last property we need to discuss about graphite is talking about its electrical conductivity, okay? Now, we mentioned when we looked at diamond that all the outer electrons of carbon in a diamond structure are locked up in bonding, so there's no delocalized electrons to carry the current. Now, that's not the case in graphite, okay? Remember, each carbon atom only makes 3 chemical bonds, so that means there's 1 electron per carbon atom that is not involved in chemical bonds, okay? So because each of these carbon atoms has one electron that's not involved in bonding. Each one has one delocalized electron. So there's one electron per carbon atom that is actually available to carry the charge if we apply the voltage to it. And that explains why graphite can conduct electricity and diamond can't. It's really due to the fact that graphite's got delocalized electrons because it's only got 3 electrons used in bonding and it's got 1 extra electron over. If we look at the properties of fullerenes, okay, well, fullerenes, they were first really discovered in the mid-1980s, and this is a famous one, a famous fullerene. This is the carbon-60 structure, and it looks a bit like a football, doesn't it? And it's made up of hexagons and pentagons. Now, you don't need to know a great deal about this, but you just need to know some of their uses. Now, fullerenes can be used for drug delivery within the body. I'm not on about it's actually transporting. It can be used to transport medicine around the body. They can also be used as lubricants, catalysts, nanotubes for reinforcing tennis rackets, so your graphite tennis rackets and graphite golf clubs and stuff like that are reinforced using these carbon fibre rich nanotubes, okay? So they can be made into different patterns as well, which some I've shown you there. So, to summarise, properties of giant covalent substances. Well, they all have high melting points and boiling points, and this is due to the strong covalent bonds between the carbon atoms, okay? Graphite can conduct electricity because it has 1 delocalized electron per carbon atom. So remember, carbon has 4 electrons in its outer shell, but only 3 of them electrons are involved in bonding in graphite, so that other extra electron is available to be delocalized, okay, if you apply a voltage to it. Diamond can't conduct electricity because it doesn't have any delocalized electrons. The structure of diamond, each of the carbon atoms is covalently bonded to 4 other carbon atoms, so all the outer electrons are locked up in bonds. And graphite, although it's got strong covalent bonds in between the carbon atoms, it only has weak intermolecular forces in between the individual layers. And because of that, it's very, very easy to remove one layer of graphite, and that's how it works in pencils, where the force of friction against the paper and the lead and the pencil is enough to overcome these weak intermolecular forces. I hope you found this video useful. Thanks.